Good afternoon, everyone. So, welcome to class 14 stochastic control and communication. So, today's will be a short class. Uh, yeah, First, let's recap what we saw yesterday. So, we're looking at problems. And first, we were interested in risk. Basically, we saw about utility functions where all the moments were involved. We were interested in information. Um, then we try to model decision-making problems as MDP problems, where in MDP problems we see that there are many policies that apply to uh, solve the MDP problem. And the policies were Markov deterministic policy, Markov randomized policy, history dependent deterministic policy, and history dependent. Randomized policy. Okay, so out of these four, we saw the for Markov deterministic policies, we saw that made an observational principle of optimality. We saw that if you the optimal policy, then the truncated optimal policy is a truncated solution, is the solution for the truncated entity, right? Using this, we came up with the algorithm known as dynamic programming algorithm, right? Then we give three examples. One example was inventory control. Second example was secretary problem. This was basically optimal stopping problem. The last one was linear quadratic related. We gained some insights by solving these problems using the dynamic programming algorithm, right? And we tried to formulate a dynamic programming algorithm for district engineering randomized policy. Here we showed that There is no benefit in randomization of a policy. No benefit in using the whole history. Basically, the optimal Markov policy implies you have a Markov optimal policy. This is what we saw. So today we want a new class of problems. So this new class of problem is basically imperfect information. So the history till now that we were dealing with basically HD S0, S0, S1, A1, S2, A2, and so on. ST minus 1, A3 minus 1, ST as the threat types, right? Here the assumption was the state is known accurate. But in real life situations, you might have systems where state is not known accurate, right? But you have some noisy or corrupted version of the state. This corrupted or noisy version of the state is what we call as information from them. Okay. So these kinds of problems are known as imperfect state equations, or in MDP, it's known as FORMDP, UMDP, which is partially observed Markov decision processes. Okay, so we'll start by writing the model. So initially what you had was you had xk plus 1 equal to fk, xk, uk, w, right? Where xk was your state at time k, uk was your action at time k, wk was the noise in the system, right? This was your state at time k plus 1. Okay. So now we have the assumption that we do not know x or the state. But what we know is we have this observation so where the zk equal to hk into xk comma uk minus 1 vk. So these are known as your observations, where these are your noise elements, and this is your state at time k. uk is the action at time k minus, because here it's not a function, it's the action is not of k, it's k minus 1, because after this observation is what you'll have xk state, and from that xk state there'll be some noisy medium or noisy channel through which you make the observation zk, and now you have the information of zk. You don't know what xk is, you know what zk is. Now using this zk you want to make a decision what your uk is. Then once you give uk, then once you give uk, the system would evolve to xk plus 1. You'll not know what xk plus 1 is, but then you'll take the xk. It will, through a noisy channel, you'll get an observation of zk plus 1. And now knowing the zk plus 1, you'll try to make a decision on uk plus 1. Okay. This is how you will, this is how your system model is. So you have this um, state dynamics and also your observation dynamics, right? So what are you trying to minimize? You are trying to minimize expectation of gn xn plus summation k equal to 0 to n minus 1 gk xk uk w. But now here, this uk, this action is not, before it used to be a strategy based on what state you are, but now based on the information that you have. This ik is something we'll introduce. This is known as the information. Right? Now, basically, by adding this new assumption, the problem becomes more interesting. And why is it interesting? Because it is closer to real life models where you have the assumption that the exact state is not known, but a noisy version of the state is known. So one of the main questions that we need to ask ourselves is, what is going to be the information? So this is an assumption in these types of model. We'll take ik equal to set of all observations till zk and actions from 0 to uk minus 1. Because you have not yet taken the uk for all k belongs to 0 to n minus 1. You don't have in. I0 is basically just Z, the zeroth observation, which you will take in action. Okay. So what we want to do is we want to find a decision rule. Now, the decision rule being mu k I k equal to u k, right? Where now your pi policy is basically all these mu k's, mu zero, mu one, so on, mu n minus one. This is your policy. But what is it that you want to minimize? Is minimize over your policies such that the expectation gnx plus mission k equal to 0 to n minus 1 gk sk mu k I k w. This is min or max, depending on whether you want maximizing or you want to minimize your cost. Right. So this expectation is over all the noise, and the noise just doesn't come from wk, but it also comes from ik, because ik has the mm, v0 noise, right? So basically, the states governing these are xk plus 1 equal to fk, xk, uk, ik, wk, and your observation zk is hk, xk, uk minus 1, ik minus 1. And these two are noises, these three. Okay, so let us closely see what happens. Suppose you're at time k, then when you're at state xk, you get an observation. This observation is basically a corrupted form of the state. So zk equal to hk, xk, ek, wk. Your wk is your noise. X is your state. Oh, sorry, this is uk minus 1. Uk minus 1 is the action you took in the previous step. Now, based on this, you update information. Now, your information is basically a vector containing, so your ik minus 1. First item, what you know, ik minus 1 is z0 to zk minus 1 and u0 to u k minus. Now, this was your ik minus 1, previous information. Now, after this information, you have updated your action to uk minus 1. So you add your new ik would be your old ik minus 1 union uk minus 1, and you've also got this new operation union z. These are basically unions, right? So now your uk minus 1 is basically z0 to zk. This zk got added. U0 to uk minus 1. This uk minus 1. Okay? This is ik. And using this, you choose action uk, which takes you to xk plus 1. And then this loop continues. So then you get new observation zk plus 1, update your information, and then you get k plus 1, and then update your state indication. So this is what is happening in this form deployment. So here, what we'll observe is here, keeping the past info is critical, right? And what we'll see that history is needed because the states are not known. So there are many differences from the previous classes, what we have done and what we are trying to do now. But there is also a similarity. There is also an underlying similarity in the classes. So what we can do is we can reduce this problem to the problems we have discussed in the previous classes. But that will increase the mathematical complexity. If you are fine with mathematical complexity, what you can do is you can reduce this problem to the previous problems, right? So what do I mean by reducing this problem is by reduction, we, I mean that all the information is taken as underlying state and then solve the optimal policy, right? So your IK plus one is IK UK Z K plus, right? So my method of action is basically I consider initial state. Suppose some initial state I consider it at time k to be ik, right? Then my action as uk and disturbance as zk plus 1. Right. So what you get is from this you get that your state at time k plus 1 is a function of state at time k, your action at time k, and your disturbance time k plus 1. So this looks a lot like the action. So your state at time k, state at time k, action at time k, noise in the system. Just here you have instead of k, it will be k plus 1, but the dynamics remain same, right? So you can model this as ik plus 1 equal to some function of k, ik, uk, zk plus 1, where this is your noise, this is your action, this is your previous state, right? So, but here there'll be a slight difference in what the properties of z. Okay, so basically you'll have probability of zk plus 1 conditioned on ik uk is equal to probability of zk plus 1 conditioned on ik uk z0 to zk. These are your previous disturbances, right? But these previous disturbances are included in ik. So therefore, z case not independent. In the previous, where we spoke about this WK, right? Where we spoke about this WK here, we had an assumption that WKs are IIT. So basically, they were independent. But here, ZKs are not independent. Okay, but ZKs are independent if conditioned on IKU. Right? This is something new that we have from the previous part. And this is a more general thing where your noise need not be independent, but they could be conditionally independent on the previous history information. And because of this history, the optimal policy that you get would be a history dependent policy, right? So the main takeaway is dynamic programming can be also applied in this general case of disturbances. And this we'll see in the next class where we'll try to apply dynamic programming to solve um, imperfect state equations or partially observable Markov disturbances. So this class was just an introduction to partially observable Markov process or imperfect state observations. Stop there.